Okay, here we have two curves. One is the raw data. You can see that it jumps around, very kind of a noisy data, right? Now, if you use the moving average, the window is, this is the window, okay? Then you can see that the slope, not the slope, okay, the curve, much more smooth. Then you can see the trend of the data, okay? So this is a very useful technique to smooth out the data. If your data has very noisy input, kind of disturbance, but that always happens in the real data. Then you can try to use moving average to smooth out the signal, okay? And it's easy to prove that this moving average is a time invariant. It's linear time invariant, and that is the proof. So I'm not going to repeat that here. It is very straightforward to prove it. Okay, got it? Okay. All right, let's jump to another important topic, convolution integral. Convolution integral. So let's look at one simple example first. Suppose we have a system. And let's consider the system. Which is a rectangular signal. Rectangular signal. Okay? And the output is a triangle. So this is the output. Right, and raise up the screen. Okay. Let's assume this system G is linear time invariant. Linear time invariant. Okay. Now, if my input signal becomes this one, okay, okay. V1. And this is output Y1. Okay? And then we call this V2. Suppose this is 1 second. Just for example. This is 1 second. Now, if I input V1 to the system, then I have the I1 come out from the system. If later on, 1 second later, I input another signal, then we call this V2, so this is V2. Okay? And then you can imagine that this will be my output. Okay, 1 second later. This will be my output. Right? Okay? It is time invariant, so I just shift and simply shift the output signal to the right 1 second, and multiply it by negative 1, and flip the signal. So this is, suppose this is 1, and then this is negative. Then this becomes output. Am I right? Okay? This is due to the variant and linear. It is linear, so I can multiply the output by negative 1, since they differ by the sign. So I can multiply the output by negative 1. And then it is variant, so I can shift the output to the right by simulate by 1 second. Oops. Yeah, that's 1 second. Now, if I have a signal which combines V1 and V2, so now this is my signal. Okay? So in the first second, my input signal to the system is 1 voltage. And then from 1 second to 2 seconds, the input voltage becomes negative 1 second. Becomes negative 1 second. So what is the output? What is the output? It's going to be the combination of these two, right? Because it is a linear system. So I can combine these two. So the output is simply the combination of the first output. So I can add them up. So the first signal is here. And then the second signal is here. And then I add them up. So I have this guy plus this guy. And then this one. So this will be my output. Okay? Now this is a very simple example, but tells us a very important concept. Because we are dealing with the linear system. So if I change the sign of input, I change the sign of output as well. If I delay the signal by 1 second, then the output will also be delayed by 1 second. Okay? That is due to the univariate system. So if I add it up, if I have a signal which is a combination, which is the sum of V1 and V2, then the output will be also the sum of I1 and I2. Okay? So this is due to the first one, linearity. So I can change the sign. This means I can change the sign. Okay, and then we have univariate. So I can take the output. Okay, so this is the basic concept we are going to implement to the next important topic. Conclusion. Any question? Any question here? All right? Okay. Okay, before I give you the details, let's look at the slide first. Okay, this is due to linearity. So I can add them up. So the output is simply I1 plus I2. And input also V1 plus V2. Then output is I1 plus I2. Okay. All right. Okay, let's look at this slide. It will be involved, but it is very, very important. This slide is very important to everyone sitting in this room. Okay, so I want you to pay very much attention. So again, let's consider a linear time invariant system. LTI is linear time invariant. Okay? So suppose I have a linear time invariant system, let me call it H. That means if the input signal is still out T, the impulse function, then the output will be H of T. Okay, that's the impulse response, definition of impulse response. All right, one more time. So let's consider a linear time invariant system. Okay, that's the assumption, very important assumption. And let's assume if I input the signal to the system, which is the impulse response, impulse function to the system, then the output is called impulse response, H of T. So H of T is due to the impulse system, impulse function to the system. Okay? So H of T is due to the impulse function to the system. Now, if I delay the input by tau second, then the output will also be delayed by tau second. That is due to the time invariant. Okay, similar to the example that we have just considered. Now, if I multiply the impulse function by a scalar, x of tau will be the input signal at tau second. And then the output will be x of tau times the impulse response, h of t minus tau, right? Because it is linear. This is a linear system. And then we multiply it by the power n, because the delta function, okay, this is the type, it should be delta, not h. The delta function is an impulse. Okay, the amplitude is infinity. So we have to multiply the tau so that we have a finite length, a finite height, one space of tau. Okay, I'll show you that again. And likewise, the output will be multiplied by the tau again. Okay? Now, if I sum up, integrate means I sum up the input signal. Then the output signal will be also the sum of all the impulse response. So, similar to what I did here. Okay? Alright, so let me show you that in detail. And that is very important one more time. And I gave you all the pictures here, but I just want to give you a little bit more explanation about what's going on here. Okay, here let's assume I have an input signal mix of P, then the output will be 1 of P. Okay, that's the assumption here. Okay, and impulse response is special of P. What do I mean by that? So if I have an impulse, so suppose I have an impulse. To the system. Then the output is H1. So this is okay, suppose if I give an impulse to the system, to this system, then the output is H of P. So that's what H of P is called the impulse response. Okay? All right. So similarly to what I did there, if I give the impulse, few seconds later, over here, okay? Then this is Q of P minus, say, off. This is the tau second, okay? Then the output will also be delayed by tau second. But the shape remains the same. So that's the basic idea. That is the basic idea. Now, let's assume my x of p is a generous so let me assume my x of t is a generous then what is the y? Okay, so what? So the idea is to implement what we have. Okay? So for the input signal, I'm going to divide it into several small strips. So the yellow line is piecewise continuous function. It's an approximation of x of t.
So let me assume the width is L. So it's L up to the 3 L, 4 L, 5 L, and so on. So this is x of 0. This is x of 0, and this is x of L. X of 2 L. X of 3 L. Okay. So my x of t now can be
Approximated by
x of 0
times. Let me use the theta to show you at least there. The third one is the
this is x of t.
okay.
And then plus.
And
This is x of L. This is 1 L. This is 2 L.
and then plus 1 bill, 2 bill, 3 bill. So,
This is x 2 L. Fine. So it's 1 L. This is 4 L.
so this x of t now can be approximated as the sum of many
Small strips.
small rectangular function set. Right? Okay? So this can okay, one more time. Let me remind you the height is of 0.
So how do I
Use mathematical function
cross it?
to represent
This function.
okay?
So this can be written as
This still have function.
at 0.
Times
Okay.
and then times x of 2. Right? And we can define this one. You can define, we can define that. Let me give you that one before we do it again. scenery street, it can be written as field. Okay, yeah. Third one, next one. T minus 2 field, and then times field. Okay, and then the third and the fourth one. Next one, 3 field. Times delta, T minus 3 field, times field. Right? So I divide the dot into small strips. Each strip can be represented by a function. Okay? But now I'm going to because I have to assume the strip is very narrow. So now I have to take the limit. Okay? Now, once I take the limit, it simply becomes an integral. Okay, so tau times Taylor function, t minus tau d tau. Now, if we consider that there's a very general case, let's assume it starts from negative infinity, otherwise we start from 0, because here starts from 0, right? But in general, this can be, the signal can be extended to negative infinity. If you want into that, be extended to negative infinity. For simplicity, let's assume we have a closed system, so we start from 0. Just for simplicity. Do whatever the time is. So here we have a closed signal and a closed system. Okay? So we start from 0. An assumption, but usually that's the case we are dealing with. So my x of t now is x of tau times delta of t minus tau d tau. Okay, but what about the output? Look at this here. Okay, so the output will be strip. If the delta is very tiny, very small, okay, then the output will be similar to that one, but multiplied by x of 0. This is due to the first strip. Okay. Then what about the second one? The second one has a delay. Okay, be careful. There's a delay. I have to delay that as well. Okay, and then x of tau. and there's a delay, 12-second delay, 12-second delay. Okay? Okay, but then I will okay. Because the other function is this one. So we have to
Assume the street has a very narrow width. So let me take the thing.
all right. So once I take the limit,
The summation
becomes integration.
becomes integration from 0 to whatever the time.
And then
H of tau, H of T minus tau.
so this is the convolution.
The new signal and the deposit slots.
Okay? All right, now convolution is useful in many applications, but when we are dealing with control systems, usually this is not a tool we are going to use. We are going to use Laplace transform instead. Okay, but this is a tool, so I have to introduce this first. And also, we can prove that this also can be written as linear. X of t minus tau, h of tau become this way. Just by changing the argument, okay, you can prove it very quickly. By changing the argument, okay? One way to do that is that. So, say t prime, whatever, equals t minus tau. So x of tau now can be written as x of t minus t prime, right? And then h of t minus tau becomes h of t prime. So you can see that now we have the form we want. The only thing you have to deal with is differentiation here. Okay? So I leave the remaining 1 or 2 steps. You can figure out that by yourself. Okay? And then we have a notation for this. We use the notation. h of t. X of t convolution or convolute h of t. X of t convolute x of t. Or you can switch the order because you can see that they are the same. You can prove it. So this also equals to okay. Any question up to this moment? Any question up to this moment? So how do we compute the convolution integral in D?
If you look at the theta,
That is very interesting. All right, in this figure, we're going to cover the thing.
and review.
Now, since we are going to so here the input signals.
And this is it. So while t is equal to u of tau, h of t minus tau,
This example that I show you here. So how do we deal with this h of t minus tau? So at first, you have h of t, that's an impulse response. And then you flip, time reversal, flip around the vertical axis. So you have h of t, negative tau, h of negative tau, right? Okay, and then
you have to
move this finger, okay, the curve, to the right by t seconds every time. And then multiply it to the u of tau. Suppose you have the input signal, u of tau here. So you have to multiply u of tau to the h of t minus tau. Okay? And then compute the area under the product of the two points. Just at one particular t, you have the area, and that gives you 1 point. So you have to keep the t, start on t,
equals 0.
1.1 second, 0.2 second, blah, 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 1 second, 2 seconds, 10 seconds, and so on and so. And eventually you can have the entire output. Okay, now let me show you one interesting. I'm not sure if you, hopefully it works. Good. So this curve is the result. It's the output curve. Okay? One more time. So this is the impulse response. You shift the impulse response to the right. Okay, and then compute the area under the product of the two functions. Then you can have this output signal. And also, if you change your impulse response, so this is the impulse response. No, this is the input signal, I'm sorry. This is the input signal for this one. Okay, let's see what happens. Okay, so the red one is the impulse response. Okay, this blue one is the input signal. So once you use a convolution, you can generate the output signal. Okay? A little bit tedious, but that's fine. Okay? Alright? You can figure it out. So again, I took this from Wikipedia directly. Wikipedia, you see that. Think about this again, because if this is the first time you saw this one, it's a little bit awkward, okay? But this is very important, I have to say that again.
All right, this is the convolution. Okay, any questions before
We move on to the next topic, next example here. Question? All right, for this example, suppose we have a system, which is a very simple system, the moving average, and we have considered this last hour. So for the moving average, the impulse response is determined by replacing the input signal by the delta function, impulse function. Okay, and you can see that. So let me show you.
So this is the moving average. So now I have an impulse function. So the output will be the impulse response.
Of B, right?
Okay. So how
To determine the impulse response. Again, we have an impulse. In 1 minute. The output is the moving average. What is the moving average in this case? So let me bring this.
So this is the
The input vector. Okay. Now, this is 0. We have a moving average, so that means we start from somewhere around here.
suppose we start from here.
Great time before 0. So this is T, this is T minus capital T. Capital T is the width of the window. If my moving average
Is in this tree.
is inside this tree, what is the output? Nothing here, right? Okay, so while T is 0,
If T
is smaller than 0, obvious. If this T is here, okay, again, moving average is
consider
one strip or one window. Okay, so let's assume we start from somewhere before 0. So here is my window now. In this window, inside this window, there is no signal at all. So the average is purely 0, right? Okay? Now,
If I move this key to, say, here,
and
T minus T plus here. So this is the string.
we are considering. Yes.
So now we have to consider the case. T is bigger than 0,
Okay.
but smaller than
And
T.
so we are considering this case. T is bigger than 0.
This is
Smaller than T. So this is the, or this is the window. If you integrate, excuse me, if you integrate
from 0 to T.
what do you have? 1, right? This equal to 1. Okay, because now the delta function is inside the window. So the integral actually is the area of this delta function. So this is 1. But if you look at the definition for the average, we have to define the integral by T, the width.
So the area is 1. Now if I divide it by T, then also I can divide by T.
So this is, okay? Now if T,
Minus T is bigger than 0.
then
Okay? So this is T. If T minus T, if T minus T, this is T. If the
left edge
is bigger than 0, then this is the window.
okay, or
Then the delta
function is not inside the window, then the average is 0. Because the nothing here, no delta function inside the window. So the output is 0. So this becomes the impulse response. So this also is the impulse response. So the impulse response for this moving average, it is simply a constant. 1 over T. Okay, so the impulse response is simply a constant, 1 over T, for T between 0 and the width of the window, capital T. And the function values is 1 over T. So this is the impulse response for moving average, Okay? Little bit subtle, but very interesting. If you figure that out, then it becomes very easy for you. Okay? Alright, I have to stop here, but we have a homework for you. Okay? That is for this example here. Okay, here is your homework assignment. We have derived the impulse response for the moving average. I need you to derive the ramp response. Rho of t, now even though there is a solution over here, but I need you to derive this by yourself. Use the concept that I showed you here. Okay? And this is ramp response, but also I need you to do this one. The step response as well. So you have to do two functions. You have to figure out the ramp response in the previous page, the ramp response, and also the unit step response. We call that S of t here. And then prove that h of t, the impulse response, actually equals to the first order derivative of the S of t and the second order derivative of rho of t. Rho of t, that is the ramp response. Ramp response in the previous page. Okay? Now let me repeat. This is this week's homework. Starts from here. Prove that this is the ramp. Okay, the ramp response. This is the ramp function. The ramp function. And then also find out the step response. Step response. If the input is replaced by unit step, we call that response S of t. So now you have rho of t for the ramp input, S of t for the unit step input, and also we have h of t for the impulse input. Okay? So you have three functions, h of t and S of t and rho of t. And then I need you to show that h of t, the impulse response, is the first order derivative of step response. It is the second order derivative of the ramp response. Okay? Got it? You can find any book. You can find any book that can give you the solution. It's fine. But I prefer you to think that before you find a solution from the book. Okay? This is much more interesting. Much more interesting. Okay? Any question before you leave? Any question? All right, then we stop here and have a good evening. Have a good weekend. Okay? You can start your term project, preliminary report for the term project. Okay? Thank you.